Hello and welcome to this video on artificial neural networks, ANN. This is really interesting since this is the foundation for all the deep learning and all the cool AI that you can see. Usually I say this for everything, but this is really interesting since you will see how the theory has been built on that you can use this yourself and understand it and know that this is just mathematics, it's not magic. Let's move on to the slides. We'll go into the theory and intuition about this. Here I am in the slides. Artificial neural networks, ANN, mathematical models with inspiration from biological neurons. Note the word inspiration. Okay, an inspiration from biological neuron. Here we have a biological neuron that I have drawn, and it's quite a simple drawing here. You have a nucleus and you have axon. Then you have dendrites. This is how the neuron looks like. And you have synapses. These are the connections here. This is a simple biological model. Okay, a simple biological model. All models, you need to know that all models are wrong, but some are useful. This is just a simple biological model of the real biological neuron. Okay? Based on this biological model, since we have simplified it much, we can look into it as we can go into how to model this with mathematics. To turn this into a mathematical model, we have something called perceptron. You can see here a lot of inputs, x1, x2 to xn. These are inputs to a neuron or a unit that does some kind of computation. And then it comes out an output. This is the perceptron model. And you can see here, okay, these are inputs, and the inputs are x1 to xn, and then you have w1 to wn. These are the connections with weights. These are corresponding to the dendrites here. These are the weights. The weights means that the bigger the weight is, the wi, the stronger the connection is with this input. That is the idea. Then you have B as a bias. This is a threshold, which will show you how it works. Then this is this unit or this neuron is a computing unit. It does some kind of function, and then out comes some kind of output that is Y. X comes in, f of x, and then we get Y. Very simple, just a mathematical function. Okay, and weighting of evidence or weighting of inputs, it means that we have these W's. These are giving the weights to the inputs. Weights of the evidence are the ones that we see or the inputs. Okay, mathematically it looks like this. If we have this function y, the output y equals to 1 if w, this weight vector, transform it and times x vector, and to transform it is just a linear algebra in order to make it work to do the multiplication. But you can see it as w1 times the x1, w2 times x2 to wn times xn. Then you add this bias term. If this is larger than 0, it means that we fire. It means that we have a signal. This is a fire. We activate this neuron. And if this is less than equal 0, then we put it to 0. Then we don't have a fire. This neuron is not working. Or is working but is not firing, this perceptron. Now it's called, we have fire and we have inhibited, and then this is the threshold. WT x plus b equals to, if you expand this, you have w1 times x1 plus w2 times x2 plus blah blah blah, wn times xn plus b. This means that, for example, if w1 is very strong, it means that these terms here become very strong. They are very important. While if w1 is small, then this term is not as important. That is the idea. You weigh them all together and add the b and see if it's larger than 0 or not. If it's larger than 0, we have fire. Otherwise, it's inhibited. Okay, for example, you have y, 1 go to school and 0 to stay home. The inputs could be like, okay, x1, it's raining, question mark. x2, it's Monday. x3 is start late. And you have for x1, x2, x3, you have these possible values, 0 or 1. This is a very simple example. Then you have the weights could look like this, -2, 1, and 4. And b equals -1, for example. Then x could look like this, 1, 0, 1, means that it's raining, it's not Monday, we start late. This is just one sample. We could have several samples, right, of x. And then we take y hat. This is the y, the estimated y, the output, equals to wt times x plus b. You have this vector times this vector, -1. It becomes -2 times 1 is -2, 1 times 0 is 0, 4 times 1 is 4. And then you have -1, this becomes equal 1, and this means that it's larger than 0. If it's larger than 0, it's a fire. When it's firing, it means that we should go to school. Otherwise, it's stay home. This prediction we made here, or this classification, is to go to school. And you can look into the weights. Okay, if it's raining, then we have -2. It means that, we don't want to go to school. And if it's Monday, yeah, it's fine. It's 1. If it's starting late, then we give it a 4. This W here, it's just me as a human. I have given it values. I have given the weights depending on what I think. What do I like based on these features here? Okay, yeah, here y equals 1, we go to school. Okay, and if we have many neurons in a network of layers, they form a neural network. This is called MLP, multi-layered perceptron. Here you have x1, x2, x3. These are the first units. This goes into the next layer, and then those goes into the next layer, and then we have outputs. It looks like this. We have input layer, we have hidden layers, and we have output layers. Similarly as before, but that was just for one neuron. We could put them together into several neurons. We can put them into a neural network. Why do we do this? Because this makes it possible to approximate any function. It makes it possible to model more complex things. This is a feed-forward network. It means that it goes forward. All the signals go forward. You start with x1, it goes into this neuron here, and this neuron, it goes to this neuron, etc. It goes one way. It goes from from input to output layer through these hidden layers and the computations. The output from each neuron goes into the next neuron. Or the output from each layer goes into the next layer as inputs. And the output from this layer goes into input to the next layer, and on and so forth. This is also called fully connected layers. Since we have full connections, you can drop off several layers for different reasons. Here, if you have hidden layers larger than equals 2, you have deep learning. You have deep neural network. We're not talking about learning yet, not deep learning, deep neural network. And the activation functions, we should know that there's some activation function, G, of this WTX plus B, some kind of nonlinear function. This is an activation function. And the output is an activation, okay? And the output is an activation of a neuron. In perceptron, we have this is the function, how it looks like. Remember what we talked about before? It's either fire or not fire. Fire means that we have 1, not fire as 0. There's some kind of threshold that makes it firing. The idea is that we want to adjust the weights and bias such that y hat gets closer to y. Y hat is the output that we get. And it should be closer to the label y. Note that this is supervised learning. We want to adjust the weights. Adjusting the weights means that we are learning, because what we did in the previous example is that I created the weights myself, or I adjusted it based on my past experiences of if I like rain or if I like Monday, etc. Here you can think of, we should adjust the weights, or we should train the weights based on the previous experience. What is the previous experience? The previous experience is the training data. So you're training the network to train the network by adjusting its weights and biases to fit the training data, the input that you put in with the labels. And the idea, you want to have small change of delta W and delta B to give small change in Y hat. In order to do this, you don't want to have this simple perceptron. Instead, you want to have another activation function, because this is quite sharp change. For example, you change in W a little bit, and then you see nothing happens, it's still 0. Then sometimes you change W and it seems to, you change W a little bit and it tips the scale. It becomes 1 suddenly, from 0 to 1. This is clearly not very good for learning, because then you don't really know how to adjust the W and B that it can change Y hat in a good way. But perceptron, it goes from 0 to 1 and 1 to 0 quite sharply. It's really hard to learn when having this activation function. That's why we should change the activation function. Training the weights and biases. You can choose other popular activation functions that work well are ReLU, rectified linear unit. Here you have x here instead. It's 0 when it's smaller than 0. Then you have y equals x as a function. And then you have leaky ReLU, that it doesn't become 0 immediately here. Instead, you have close to 0, and then you have y equals x. Then there's swish function. The different activation function to choose, this is a hyperparameter. We're talking about hyperparameter tuning again. And as you've seen, now you see that, the machine learning stuff that we learned before, it's still useful here. You can connect the dots. You can connect that, this is an activation function. It's a hyperparameter. This we need to tune. We need to know in order to know which one we should choose. Then, when we're training weights and biases, we need to have a cost function. We use a gradient descent algorithm. The cost function, what is that? You have seen loss function before. You have seen the error, some kind of error that you want to minimize. It could be like RSS, residual sum of squares, as in when you're working with linear regression. And when you're working with, for example, random forest, you have the Gini, or decision tree, you have the Gini index for when you're growing the trees for classification, for example. And in classification, many algorithms you may have used, let's see, recall, F1, accuracy. These are different these are different functions that you want to either maximize or minimize. And here in ANN, we have cost function, a cost function of W, B, cost function that we want to minimize with respect to W, B. W, B is the input parameters. Those are, or not input parameters, but these are the weights and biases that you want to change in order to have this cost be low as possible. And the cost is some kind of error. We want to find weights and biases to get loss as small as possible. You want this C to be as small as possible. And you need to approximate the solution by taking small steps in direction where the loss decreases the most. And these small steps are the learning rates, and where it decreases the most is the gradient. You're doing a gradient descent. This is the gradient descent algorithm. And you may have heard of stochastic gradient descent also. You take small steps. There is variations of this gradient descent, but basically the gradient descent is that you want to go down a mountain of error to find the least error. In order to do that, you find a gradient, which is basically a derivative in multiple dimensions. You go towards that step. You go towards the negative of the gradient. Then we talk about gradient and backpropagation. Here you can see it as a mountain of errors, where you start in the top where you have quite high error, and then you go down in the slope, and you go down in the slope, go down where you choose W and B to find where it's the sharpest, where it decreases the most. You take a small step there, you take a small step, you take a small step until you reach the end where you have least error, and then you have learned enough. That is the idea. This is the minimum. Analogy: choose steepest slope and take a short step in that direction. Repeat this until you reach the bottom. This is the analogy. And in two-dimensional case, you can see it as this. You have an error here, you have W1, and you have a slope that looks like this. You start here, and then you follow the derivative until you reach the end. The learning rate, it determines how long this step is. If you have short learning rate, then you have a short step. Then it will take longer time to train, but it means that you learn more. When you're learning more, doesn't mean that it's necessarily very good, because if you learn a lot, you may learn all the noise that exists in the data, which means that you're clearly overfitting the data. You have too complex models, then you need to think back into the lecture where we talked about bias variance trade-off. You need to increase the bias and decrease the variance, that you need to simplify the model in different way. Then we have stochastic gradient descent, which I talked a little bit about before, and mini-batch gradient descent. They are popular variants of this. For neural networks, we have many layers of neurons. In order to do this, to learn, we need to propagate backwards layer by layer and compute the gradient descent to update weights and biases. This is called backpropagation. In this video, I won't go through backpropagation since this is quite a large topic. I might cover that in another video, but for this video, it suffices. In this video, I hope that you've gotten some intuition about the ANN and what that is. We've gone through an example of how we start with a biological neuron that I've drawn as a model, and going into the perceptron. There we gone through a very simple example of how to compute using this perceptron. Very fun example, but it's up to you to decide. But the weights that we've chosen was based on my own experiences. But how would the artificial neural network or the neuron or the network learn these weights? That is based on the training data. We've gone through that, and we've gone through the multi-layered perceptron. We put in several of these neurons into a layer, and then to get a feed-forward network. This is in order for it to learn more complex patterns in the data. Then, in order to learn from in a multi-layered perceptron, you need an algorithm called backpropagation. Then it means that you're going backwards to learn. We haven't gone through backpropagation in this video. That I will save for probably a future video. But we've gone through gradient descent and how it would work when we learn for learning these weights and biases, because these are the ones that you want to adjust in order to fit the training data. Then we talked about gradient descent, and talked about how we go down to find the minimum of the errors. I hope that this wasn't too much mathematics for you, but I needed to keep some math in order to make it more understandable, and to see that these artificial neural networks it is just linear algebra and calculus in the end. I hope that you've learned a lot from this video, and see you in the next one. Bye.